Hello. Now this is the video related to motion in a plane, and as we are finished with the vector part of it, we'll be continuing with the projectile motion. Now the term projectile is it means a certain object which is projected, and obviously it is projected to to an empty space. Now the we are to study the motion of it, obviously. So the chapter is as a whole has the phrase projectile motion. Now the projectile that is to be projected can be projected in various ways. In the kinematics section, we had discussed that we can have a vertical projectile, that is, a particle is projected from the ground up into the air, and then it travels back, obviously along the same line. Just to show you, I have drawn a different line by its side, but it obviously comes down along the same line after reaching a maximum height. Now maximum height is the point where if we have started it or given it a velocity of u, obviously the velocity at this point gets zero. The velocity or the speed, the magnitude, it becomes zero. And why does it become zero? It becomes zero because of the gravitational pull, the acceleration due to gravity, which acts in the downward direction. And as a result of that, the gravitational acceleration acting in the opposite sense of its motion, the velocity is decreasing. That is, the body is obviously experiencing retardation or deceleration, that is negative acceleration. Now on reaching the maximum height, the gravitational acceleration or the gravitational pull still continues to act, obviously, and as a result of that, what happens is that this object starts coming downward, and as it comes downward, it starts gaining some speed, and on reaching the bottom it has a certain speed. Let this speed be u dash, which is the initial speed while it is moving in the downward direction, and v dash be the final speed as it reaches the bottommost point, which is obviously the point from where it was projected upwards. And this entire, let us say, it travels through a distance x, through a distance h along the vertical direction. Now we had already discussed this, but still it'll help you get a brief idea about what we are about to discuss in the other cases of projectile motion. Now in this case, you have in this entire phenomenon, you have an ascending case, that is while ascent, and a descending case, that is when it is descending. So we'll be considering the cases when it is ascending, during ascent, and during descent. Now during its ascent, obviously the velocity is decreasing. That means the final velocity is zero. The initial velocity was something finite. The acceleration obviously was minus or the negative of g, and that is why the final is zero. Final velocity is zero, and the displacement obviously is h. And now we are concerned about the magnitude only in this case, as far as this this part of the theory is concerned. So we can just relate the equation as we have the third equation of motion, that is v square minus u squared is equal to 2as. And so from that, what you have is 0 squared minus u squared is equal to 2 times of minus g times of h. So h here can be calculated, and as you can see, it depends on the square of the velocity with which it was projected into space. So that means, had it depended directly on the velocity instead of its square exponent, then we would have had a straight line equation, that is the acceleration would have been 0 in that case. That means the graph would have been just a straight line. But the as the displacement here, that is h, is dependent on the square of the speed, so that is why you have a varying speed. The distance varies as the square of speed, and hence we can relate it to a uniformly accelerated motion. All of this has been already discussed in the kinematics section. The graphical analysis and everything about it has already been discussed, so you can check for that in that section. Now if we consider the descending part, so during descent what you have is u dash, which is obviously equal to 0. That is the final speed v during ascent. And the all you need to find out is v dash. In this case, the height or the displacement obviously remains the same, but the acceleration here I can say is positive as it is moving downward. We will consider the vector case of it, where we will be taking the acceleration completely negative during its entire motion, but as of now we are considering the acceleration to be positive in one part, that is in the descending case, and negative in the first part. So the acceleration being equal to g, what we have over here is that the displacement is obviously the same, that is h. So finally the final speed v dash squared is equal to u dash squared plus 2 times of g times of h. Now h obviously, as you know, has the value as we have determined here. H is equal to u square by 2g. So finally what you have over here is v dash squared. Now the u dash squared is obviously equal to 0 because u dash is 0 over here. So v dash squared is equal to 2 times of g times of u square by 2g, which was the value of h that we had obtained. So the 2g's can get cancelled, and finally you have v dash squared is equal to u square, or v dash is simply equal to u. In case of magnitude, we are only concerned about the number, that is the value, that is u. That means the velocity with which it was projected into the vertical direction, in the vertical direction along the straight line path, is the velocity that it has achieved as it reaches the bottom. And why not? Because the initial velocity and the final velocities in those cases had a value, the values were fixed and were just interchanged for the interchanging condition during descent. That is, the acceleration was negative in the first case and positive in the second case. So obviously you will be having the same thing every time. Now you can obtain the time that it takes for the object to ascend to that height and the time that it takes to descend through the same height, and as quite evident, the times will obviously be the same because the limits of the speed are just interchanging on either ways with the change in the direction of acceleration. So obviously you will be having the same time limit, but let's just check for ourselves if the times are the same. So let t1 be the time of ascent, and how to calculate that? V is equal to u plus at as we know it. So the v in this case is t is obviously the time of ascent, and as we have v is equal to u plus at, instead of a we can just write g, but the g is negative in this case because it is ascending, and t1 is obviously the time taken. So with v being 0, we have a minus of u to be equal to minus of g t1. So t1 is simply equal to minus u divided by minus g. So this is simply equal to u by g. Obviously the time cannot be negative, so the time is u by g. Now another case where during descent what we find is that v dash is equal to u dash plus a here is equal to plus g, and the time taken is supposedly t2, and so v dash was obtained to be u dash is as we know it is 0, and that is equal to g times of t2. So t2 is obviously here equal to u divided by g, which is exactly the same as in the ascending case. Now the total time of flight is the time that it takes for the projectile to stay in air, and so the total time of flight in this case is simply the addition of both the times that it stays in air, and as both of them are the same, so we have two times of either of the time, that is ascent or descent, so it is equal to 2u by g. Now there is no motion along the horizontal line in this case, and so we do not have a horizontal range, but that is exactly the thing that we are going to discuss. The extra bit that remains if in this bit that we are going to study, the horizontal range is what we are going to experience in this case. But before that, we can take certain cases. One of the cases is that of the horizontal projectile. Now the horizontal projectile is when the particle or the object is any object is projected along the horizontal line from a certain height supposedly. Now we have a certain height h. Once again we are taking it as h, and from that height we have an object to be projected with a initial speed u along the forward direction. Now as it is projected in the forward direction, we neglect in obviously we are doing this in our space, that is our atmospheric within our atmospheric blanket. But had it been in space, there would have been no air or any molecule to really disturb it, so it would have moved perpetually along that line. But because we are doing it in our atmosphere or in our real life, practical world that we experience on a daily basis, we experience certain forces that are associated with it. One of them obviously is the gravitational pull. Now this gravitational pull acts in the downward direction and just drags it downward. And in case of the forward motion, however, we for our convenience we can neglect any form of air resistance or any air molecule obstructing its motion as such. So the projectile continues to move in the forward direction with a velocity u which is constant along that line. However, initially along the y direction the initial speed was probably 0 because there was no such velocity that was given to it along that line. So along the downward direction it had no velocity, but however, because of the gravitational pull, it is dragged in the downward direction and it is attracted. Now as it is attracted in the downward direction, the motion of the object is somewhat like this. Instead of the horizontal motion that we could have experienced in space, we just experience a certain parabolic motion along this line, that is along this line that I have just ticked, because of the gravitational pull. A combination of the forward directional motion. Now obviously the forward direction that it travels is the horizontal range, that is the extra bit that we are going to determine, and this horizontal range is only because of this particular component, this particular thing that is pushing it in the forward direction. In the downward direction, however, it takes a certain amount of time to move, to displace from the topmost point to the bottommost point. And in that process, as it moves downward, that time multiplies, or that in that time this component drags it or pushes it in the forward direction that we had given. Actually it is the only speed that we had provided. This speed however got built up along the y direction, and now it has a certain velocity vy as it reaches the ground. Obviously the certain speed that with which it reaches the ground is not exactly here but here, that is vy is along this line, and u, that is the speed that it was provided with, is along the forward direction. Now it would have continued with the speed u in the forward direction had it not reached the ground. After this it can bounce or do anything, but we are not concerned about the motion after that. We are concerned about the fact that we are concerned about the motion from the topmost point, that is here, till the bottommost point that it reaches the ground over here, and thereafter it can bounce, or if it's on a you know um, inelastic collision type of case, then it may just dip in there, that in case of water or sand on any kind of surface that it is falling on, if it's solid ground, obviously it will tend to bounce, but those are separate cases to be studied later. We are just concerned about those two limits, that is the uppermost point and the bottommost point over here. Now as far as the time is concerned, the time obviously will be the same during descent, because here that t2 that we had obtained over here towards the right hand side of your screen, that you can see the t2 is the time taken for any object to move from that topmost point where it had no vertical velocity, because in this case as well on the right hand side it had no vertical velocity as it reached the topmost point. Obviously this is a different case, but the scenario is somewhat similar. So uy there being equal to 0, the time taken obviously will be something which is equal to u by g, but obviously you do not have a u in this case. U is here in the forward direction. So what about the time? The time here will be in the form of the height, or can be expressed in the form of height. That is, from the equation s is equal to ut plus half t square. So now h, that is the vertical displacement, is equal to ut, I take the time as t over here instead of t2, uy into t plus half g, because the g is positive in this case in downward motion, t squared. Now uy, as you know, it didn't have any velocity along the downward direction, so uy is simply equal to 0. So you have the value of t in this case to be equal to, now t squared, I'm writing it, t squared is equal to, the 2 gets cross multiplied with h and g goes to the denominator, and finally you have t to be equal to simply 2h by g. That is the time taken for the object to reach the ground, and it is exactly the same time for which it will remain in air till it strikes the ground at this point that I just encircled. Now in that time it is moving with a constant speed u in the forward direction, and that is what is responsible for that horizontal range. Now the horizontal range in this case is a non-accelerated motion, and that is why you have a constant speed over there u multiplied with the time taken t. So u multiplied with t is simply equal to the distance traveled along the horizontal line, which is equal to u multiplied with 2h by g. So this is the range that it covers along the horizontal line, and that is only because of the horizontal component or the horizontal speed that has been provided, which is constant. We are neglecting air resistance in this case, as discussed earlier. Now in this case of a horizontal projectile, we didn't involve any kind of angle, but let us say, if what if the case is that we have a projectile which is projected at a certain angle with respect to the horizontal. Now in this case what we have over here is that, let us take the dotted or the dashed line that I'm drawing just now as the ground. It's obviously pretty straight. And from that ground level, what we are doing is we are projecting a particle. We are projecting a particle into space, and that obviously from our common experience what we know is that it is going to take this kind of a path, this kind of a trajectory. The trajectory is the path that is taken by the object. Now this object was projected supposedly with a speed u along that line, and it reached a maximum possible height, let that be equal to h max, and thereafter it obviously took the downward motion. Now we can just say that let us say that this was projected at an angle theta with respect to the ground. So we have two components of speed over here. U cos theta acts along the horizontal direction. At every point it is the constant value that with which it moves in the forward direction. Remember, in the forward direction, in this case, we are always neglecting any form of air resistance, and hence we cannot really expect any object or anything else to resist its motion or cause any form of deceleration or anything that is applying a certain force on it to aid its motion, that is any form of acceleration or deceleration is neglected. Now the u cos theta obviously is constant at every point. Here also it is u cos theta. Here also it is u cos theta. Every possible point that you see on that trajectory, on that line that I've just drawn, the u cos theta remains fixed, and you know why. Now there's another component which is the vertical component, and that is u sine theta. Now u sine theta is the one responsible for taking it upward initially, but the gravitational pull keeps on acting in the downward direction throughout the motion, and as a result of that it reaches a maximum height where the u sine theta component has decreased to Vy, that is equal to 0. Let us say this is Uy, u sine theta, but that decreases because of the gravitational pull in the downward direction, and now it has achieved a maximum height where the vertical component of the speed is 0. Now because this vertical component of the speed has become 0, that is why the height is maximum over there, because had there been any amount of speed left in the vertical direction, it would have continued to move upward, but there is no speed left. The speed has decreased to 0 or reduced completely to 0. Now the only option available for the object is to move in the downward direction, and what provides the speed in the downward direction gradually is the gravitational pull once again. And so here it can be said uy dash is the initial speed for the downward motion, and as it reaches to the bottommost point over there, the speed has become vy dash, which is something finite. Now again we are considering the motion up until that point, that is as it reaches the ground. We are not concerned about any form of motion that is taking place after that. So as you can say, or you can predict now, is that this u cos theta, which is constant over here as well, that would have taken the object in, or that will be responsible for taking the object in the forward direction, because if only is the case that the object remains in air. But here we have reached a ground or a bottommost point where we are considering the end of our of the motion, so we need not be concerned about the u cos theta taking it in the forward direction after that. Now it will obviously have a resultant. this resultant velocity will be somewhat in along a line which is lying between this u cos theta and vy dash, because it will be a resultant of both of them. Now we just need to express the parameters with respect to one another so that we can study about the motion of any object given to us. So if u sine theta uy was the component responsible for taking it upward, so the time of ascent obviously will be equal to uy divided by g, and that is equal to u sine theta divided by g. Why? Because it was the case we had studied over here in the right hand side of your screen. On the right hand side you can see t1 is the time of ascent and t1 is equal to u, that is the speed that was given in the upward direction in this figure that we have over here at the top right corner, and that was u in that case. Here it is uy or u sine theta. Similarly, you can now predict the time taken, that is t2, that is the time of descent, and the time of descent will obviously be equal to the time of ascent, and that will be simply equal to u sine theta by g, which was the case at the bottom right corner of the screen that you see t2. Here there it was u, here it is u sine theta, the component of u. With these times available, now what we can do is that we can just obtain the value of that maximum height that it reached. Now the maximum height that is reached by it is obviously okay, you need not use that time. What you can do is just vy squared is equal to uy squared minus 2g h max is the maximum height, so let that be the case. Now that will be equal to this minus uy square, can obviously this is 0, minus uy square goes to the left, minus uy square by 2g by minus 2g is h max. So h max simply is equal to the maximum height being uy squared divided by 2g, or uy simply is u sine theta, so u square sine squared theta divided by 2g. Then after achieving that maximum height, obviously it will be traveling downward, and the displacement along the vertical line while downward motion will be the same as the displacement during upward motion, which is h max. It will be the same in both the cases. So h max being same, what we can say is that we can obtain a vy dash. Vy dash squared is equal to uy dash squared plus 2g h max. We know the value of h max now, so vy dash squared is simply equal to uy dash squared is 0 because that is the final velocity of the upward motion, so that is 0, and what you have is 2g, and h max was u square sine square theta divided by 2g. The 2g's get cancelled out, as the case over here on the right hand side of your screen. That is exactly what we are getting over here, but instead of u, you just have a u sine theta. So this is simply equal to u square sine square theta, or the root over of it. Let me just write it in the next line. Vy dash is equal to u sine theta. So again, you have the velocity at the bottommost point to be the same as the velocity as with which it was projected initially along the vertical line. It was projected at an angle, so we have the component of that velocity over there. Now with u sine theta in the downward direction and u cos theta along that horizontal line, the angle between them is obviously 90 degrees over here. So you have a resultant velocity. Let this resultant velocity be Vr. We are concerned about its magnitude. Vr mod is equal to the square root of the square of each term, that is ux squared plus vy dash squared, which is giving me Now, because you have x squared to be u square cos square theta and vy dash squared is equal to u square sine square theta, the u square can be taken common, and you have cos square theta plus sine square theta to be equal to 1, and the root over of that is obviously giving you u. So that is the exact speed, at least magnitude wise, that you are getting when we have the object to be reaching the bottommost point, which is obviously in the same level as with which it was projected into the space. If the levels are above or below that, you will have different value of vy dash, and as a result of that the resultant will be different. But for the same level that is outlined by that dashed line over there, for the same level obviously the resultant will obviously be the same. Now what we want to know is the horizontal range. The horizontal range is obviously because of the u cos theta component of the velocity which is dragging it in the forward direction, and that is constant, and that when multiplied with time is going to give us the horizontal range. So the horizontal range in this case r is equal to u cos theta, which is the velocity along the horizontal direction, and the total time of flight. Now the total time of flight in this case is u sine theta by g during ascent and u sine theta by g during descent. So it is simply the addition of both of them, that is 2u sine theta divided by g. Now because you have the value of let me write the g properly over there, because you have the value of u cos theta and u sine theta, the 2 times of sine theta times of cos theta is a trigonometric identity which is sine 2 theta, and the u's can get multiplied to give u squared, and the 2 sine theta times of cos theta is simply sine of 2 theta divided by g. So this is the value or the magnitude of the horizontal range traveled by that object. So this is one part of it, that is the projectile. Now you can have various cases in this where the object when projected from a height, just like in the first case, and if it is projected at an angle, then the phenomenon will be something, a mix of both of them. That is, let me just add another page. Right, you can have cases when it is projected from a certain height. Let us say, let's take it as h again, and it is projected like this with an angle. Now the angular projectile, as you know, as discussed over here, it will take a trajectory and it will reach over here. As it reaches over here, it will have the same speed with which it was projected in the downward direction, in the upward direction. It will have the same speed, but the velocity obviously changes because there is a change in direction. So the magnitude remains the same, the angle changes, but as it continues to move, right, you have both the components of the velocity. Now here it was vy dash. Now it is something else now, as because the acceleration still acts in the downward direction and the velocity keeps on increasing in the downward direction. So maybe here you have vy double dash or something like that. It's a different magnitude along the vertical line because the gravitational acceleration keeps on accelerating the object. But in the forward direction, obviously, you have ux, that is u cos theta. Now, so it depends on the height and the case that has been provided to you. Now, if you remember, I had discussed, or I had just said that in case of displacement of an object, you can consider the acceleration to be negative completely. That is, supposedly the case where we had taken the object to be projected in the upward direction vertically, and then it comes back along the same line. Now in this case what you have is that as it reaches the topmost point, the displacement is maximum over there, suppose S, and then as it takes its way back to the ground, at any given time you will have a final displacement. Final displacement is obviously, let the object reach over here at a time t, and the final displacement here is simply, let me take it as h, so final displacement here is simply s. So vectorially it is easier for us to consider the case where displacement is equal to u t minus half gt squared. G here is always acting in the downward direction, as obviously. So with this equation you can calculate the net displacement of the object at any given interval of time, or at any given instant of time. So you'll be you'll have a good idea about this entire thing that I've just discussed with the numericals that we'll be doing in the numerical section of it. But as of now, theoretically speaking, this is just the ideal equation to determine the displacement. You could have, however, determined the displacement by knowing the total time and then subtracting the time that it takes from the topmost point up till here, and then you could have just obtained the displacement for that, and or the distance covered for that, and then you have subtracted from the maximum height. But that's a very tedious thing to do. The easiest way to approach such kind of questions is just to use the velocity equation. Now the in this case that we have over here, up until the same level, as you can see over here, that the final velocity that it achieves has the same magnitude, but definitely the direction is changing, and the direction, let it be some angle alpha with respect to the horizontal. Now remember, it was projected at an angle theta with respect to the horizontal. Now the angle, let us say, is alpha with respect to the horizontal, obviously below the horizontal. In this case, this angle is simply alpha. So in that case we can determine the alpha, that is tan alpha equals the vertical part of it, that is Vy dash, divided by the horizontal part of it, that is Ux. And so what does that give us? U sine theta, because the magnitude was the same as the initial case, and U cos theta over here. So the U's can get cancelled. Sine theta by cos theta is tan theta, which is tan alpha. That means alpha here is equal to theta. That means it will dip by an angle theta, which is the same as the angle of projection. So everything about this is same. The angle of projection is equal to the angle with which it is dipping into the ground at the same level, obviously horizontal level, that is. The speed along the vertical line, they are the same. The speed along the vertical line remains the same, only with the change in direction exactly being opposite. And the u cos theta, that is the horizontal component, remains constant at every instant of time during motion, neglecting air resistance and any such cases of acceleration, deceleration along that line. With all this available to us, we can now discuss about the equation which tells us about this trajectory that it takes, and that is why it is known as the equation of trajectory. Now the equation of trajectory simply relates the displacement along the x direction with the displacement along the y direction. Now let at any instant of time, let us take this kind of a projectile, that is the one that we had discussed just before this. It is projected with a speed u at an angle theta, and let at any instant of time it has traveled through a distance x along the horizontal line and y along the vertical line, right, such that its coordinates are x and y. Now remember, this is motion in a plane, so we are considering only two axes, and this is in some instant of time t. Now at that instant, obviously the horizontal part of the velocity is intact, that is u cos theta along this direction. U sine theta, that was initially the case over here, has decreased to some extent as a result of the negative acceleration along the vertical line. So what is that value? The displacement in the y direction is simply equal to y, that is the displacement, s is equal to ut plus half a t square. So y is equal to u sine theta, that is the velocity in the vertical line, t minus half g t squared. Why minus? Because the acceleration is negative, as I discussed. Now how does this relate y with x? Because we know that along the horizontal line the displacement has been x in the given time t. We know that the speed remains constant along that line, so x simply is equal to u cos theta times of t. That means t has to be equal to x divided by u cos theta. With that available to us, we can just apply this value over to the first equation over there. So we have y to be equal to u sine theta, and instead of t we can write x divided by u cos theta minus half g x divided by u cos theta squared. And what does that give us? U's can get cancelled over here. X times of sine theta divided by cos theta is tan theta minus half g. Instead of that entire term, I can just take the u square cos square theta in the denominator over here, and I keep the x square outside. That now relates y with respect to x and is what is termed as the equation of trajectory. Now in this equation, what we get to know is that the path is parabolic, because y here is varying with respect to the square of x, and that is why you have the equation to be that of a trajectory, and the equation that to be as that of a parabola, with all these terms in the bracket remaining constant, because u is constant, theta is constant. U being the initial speed, the value of initial speed remains constant. Theta is constant, the value of the angle, that is g is constant. So everything in that bracket is constant, but it is varying as the square of x. It is also, we have a term over there, x tan theta. The negative symbol over here for x square suggests that y is varying as the convex parabola in that case, that is the curved part of the trajectory facing downward. Had this been positive form of x squared, then we would have had a cup-like or a bowl-like shape of that parabolic path, but that is not in case of the gravitational motion that we are discussing right now. That is completely out of topic in this case. That is not acceptable. So obviously you must have a minus sign, so that is a hint that the shape of the parabola is facing downward. So from this equation of trajectory, at any given instant of time, at any point for a given value of x, you can determine the value of y and vice versa. with the angles and everything available to us. So that's a complete video on parabolic motion. There is more to it which we can discuss in the numerical section, as we will be doing later on for this motion on a plane. But that's it for the projectile part of it. We'll be discussing more on the motion in a plane topic, but that is for the upcoming videos. Till then, thank you for watching.